Let's return to a word problem that we looked at earlier. This is the one with the patient in the hospital that had to have at least 84 units of drug A and 120 units of drug B each day. And we said each gram of substance M contained 10 units of drug A and 8 units of drug B. Each gram of substance N contained 2 units of drug A and 4 units of drug B. Now suppose that M and N contain a slightly harmful drug W. And let's say there is 3 units of drug W in each gram of drug M, or actually I should have said substance M, and 1 unit of drug W in substance N. How many grams of substance M and N can be mixed to meet the minimum daily requirements of drugs M and N? And at the same time, actually that should say the requirements of drug A and B, so I need to correct this. At the same time, now we're going to return to a word problem that we looked at earlier, but in this problem we're actually going to have an objective function. So earlier we talked about this patient that needed to have at least 84 units of drug A and 120 units of drug B each day. And each gram of substance M contains 10 units of drug A and 8 units of drug B, while each gram of substance N contains 2 units of drug A and 4 units of drug B. Now suppose that both M and N contain a slightly harmful drug W, and there is 3 units of drug W in each gram of substance M and 1 unit of drug W in each gram of substance N. So the question is, how many grams of substance M and N can be mixed to meet the minimum daily requirements of drugs A and B and at the same time minimize the amount of drug W? So we set up the constraints earlier, and so if you need to, go back and look at that video, but we came up with 10x plus 2y must be greater than or equal to 84, and that satisfied the drug A requirements, and 8x plus 4y must be greater than or equal to 120, and that satisfied the drug B requirements, and of course x and y had to be non-negative. Now we need to introduce an objective function, and notice that the total dosage of drug W can be represented as 3 units from each gram of substance M and 1 unit from each gram of substance N. If you go back and take a look at this, you'll see that there are 3 units of drug W in each gram of substance M and 1 unit of drug W in each gram of substance N. So that's how I got this formula. So we want to minimize the amount of drug W, which would be 3x plus y, subject to this constraint. Now, we graphed this earlier, I think, maybe not, maybe we didn't graph it earlier, so let's go ahead and graph it. So if you let x be 0 and divide 84 by 4, let's see what we're going to get here. I had to correct a little typo here. That should be 10x plus 2y equals 84. So if you let x be 0, divide both sides by 2, you get y is 42. And if you let y equal 0 and solve for x, you get x, 10 goes into 84, we'll just say 8.4. So the x value would be 8.4. The other constraint, the boundary would be 8x plus 4y equals 120. So if x is 0 and you solve for y, you get 30 for y. Then if you let y equal 0 and solve for x, you get 15 for x. And so we can use those values to plot the points. Now, this first line goes through 0, 42, and 8.40. So let me see if I can show you that. I actually don't have the 8.4 listed, but obviously the 8.4 would be less than this point here, the 15. So there's your point 0, 42, and down here's your point 8.40. And if you draw the line through those 2 points and then shade the appropriate direction, if you test 0, 0, you'll get a false statement. So you have to shade the outermost region of that. So basically you would shade this side of that particular line. Let's see, where's it? So you would shade that side of that line. And then the other one actually goes through 0, 30, and 15, 0. So 0, 30 is like right here, and then 15, 0 is right here. So you see I drew the line through those points right there. And then, of course, if I test, I'll get a false statement again. So I'll have to shade this side of that line. Okay, now your shaded region, your overlap, would be the region that's farthest out here in this area. And of course you have to remain in the first quadrant because x and y are both greater than or equal to 0. So let me see if I can lay some boundaries down for you. So it would go from here down to here, and then it would switch directions here, and then it would go down to here, and then it would follow the x-axis there. Now let me see if I can highlight that for you to give you a better picture. So make it blue, we'll make it thicker. Okay, so now you can see the boundary here. Now the boundary comes down here, and remember this point right here where it changed, this corner point was the point 0, 42. And then of course down here, this point where it's changing is the point 15, 0. And this point is just the intersection of the two equations. So if you find where these two equations here intersect, you should get the point 422. And you can check that if you want to. 10 times 4 is 40. 2 times 22 is 44. 40 plus 44 is 84. And then 4 and 22, 8 times 4 would be 32. 4 times 22 would be 88. 32 plus 88 is 120. So 422 is the point in between. So we get three corner points, the 0, 42, the 422, and the 15, 0. And we want to plug them into the objective function 3x plus y. So notice if you plug 0, 42, in other words, if you don't use any substance m and use 42 units of substance n, then you'll get 42 units of drug A. If you use 4 units of substance m and 22 units of substance n, that'll give you 34 units of drug W. And then if you use 15 and 0, that'll give you 45 units of drug W. And remember, we wanted to minimize the amount of drug W, and the way to do that would be to use 4 and 22, and that would give us a minimum value of W of 34 units. So the optimal solution would be a minimum of W equals 34 at the point 422. And I kind of stated what I have here not quite correct. It should say 4 units of substance M and 22 units of substance N, not drug M and drug N. On these next two problems, I'm just going to set these up for you, but I give you just a real rough sketch of the graph over here, but if you want a better sketch, you need to do it on some graph paper. So let's take a look at setting up a couple of word problems. Here we have a manufacturer of dog food that makes 2 secret ingredients that goes into their dog food, and they codenamed it Superdog and Underdog. Each kilogram of Superdog contains 300 grams of vitamins, 400 grams of protein, and 100 grams of carbohydrates. Each kilogram of Underdog contains 100 grams of vitamins, 300 grams of protein, 200 grams of carbohydrates. The minimum nutritional guidelines require that a mixture made from these ingredients contain at least 900 grams of vitamins, 2,200 grams of protein, and 800 grams of carbohydrates. Superdog costs $2 per kilogram, and Underdog costs $1.25 per kilogram. Find the number of kilograms of each ingredient that should be produced in order to minimize cost. So the first thing I'm going to do is state that I'm going to minimize my costs, and if I let my x1 be the number of kilograms of Superdog that we use, and x2 be the number of kilograms of Underdog that we used, well, we know it's going to cost me $2 per kilogram of Superdog plus $1.25 per kilogram of Underdog. Now the constraints that I actually have to have at least 900 units of vitamins. Now if you go back up here and read the problem, you'll see that each kilogram of Superdog will give you 300 units of vitamins, and each kilogram of underdog will give you 100 units of vitamins. So 300x1 plus 100x2 is the total amount of vitamins, and that has to be at least 900. It also says we have to have at least 2200 units of protein. And if you go back up there and read, you'll see that each kilogram of Superdog gives you 400 units of protein. Each kilogram of Underdog gives you 300 units of protein. So total protein is represented by 400x1 plus 300x2, and that has to be greater than or equal to 2200. And then we have to have at least 800 units of carbs. So if you go back and look at the problem, you'll see that each kilogram of Superdog must have 100 units of carbohydrates. Each kilogram of Underdog gives you 200 units of carbohydrates. So 100x1 plus 200x2 is the total units of carbohydrates you get, and then it has to be greater than or equal to 800. And then, of course, you also have to have your non-negative constraints here, because the number of kilograms of Superdog and Underdog can't be negative. Now, I've sort of partially worked this here for you. So you go ahead and graph this, and your graph should look something like this, and you'll get 1, 2, 3, 4 corner points, and the corner points are 0, 9, 1, 6, 4, 2, and 8, 0. And then when you plug in the corner points, you should get a minimum cost of $9.50. Okay, so I'll leave you to do that. This would be a good problem for you to practice the graph on. And I gave you all the intercepts for each of the equations here, and the testing for the to see which side to shade and so forth. You just need to do the graph. Okay, now the next one says a chemical firm makes 2 types of industrial solvents, S1 and S2. Each solvent is a mixture of 3 chemicals. Each kiloliter of solvent 1 requires 12 liters of chemical A, 9 liters of chemical B, 30 liters of chemical C. Each kiloliter of solvent 2 requires 24 liters of chemical A, 5 liters of chemical B, and 30 liters of chemical C. The profit per kiloliter of solvent 1 is 100. Profit per kiloliter of solvent 2 is 85. The inventory of the company shows there's 480 liters of chemical A, 180 liters of chemical B, and 720 liters of chemical C available. Assuming the company can sell all the solvent, find the number of kiloliters of each solvent the company should make to maximize profit. Okay, so again here, the first thing we do is we realize we want to maximize our profit, and our profit function would actually be letting x1 be the number of kiloliters of solvent 1, x2 the number of kiloliters of solvent 2. Profit would be 100x1 plus 85x2, because it tells us we profit 100 off of each kiloliter of S1 and 85 off each kiloliter of S2. Now, since we only have 480 liters of chemical A available, we got to make sure we stay within that number. So the actual chemical A we use must be less than or equal to 480. So think about, how do we use chemical A? We use 12 units of chemical A per kiloliter of solvent 1, and we use 24 units of chemical A per kiloliter of solvent 2. So the total chemical A used will be 12x1 plus 24x2, and that has to be less than or equal to 480. And similarly, for chemical B, we only have 180 available, and so we use 9 units of chemical B per kiloliter of solvent 1, and 5 units of chemical B per kiloliter of solvent 2. So 9x1 plus 5x2 must be less than or equal to 180. And then lastly, for C, there's 720 units available, and we use 30 units per kiloliter of solvent 1, and we use 30 units per kiloliter of solvent 2. So 30x1 plus 30x2 has to be less than or equal to 720. And then also don't forget your non-negative constraints. Now again, I gave you kind of the rough graph of this, and you can see I've got a corner point here, a corner point here, a corner point here, and a corner point here. So there's 4 corner points, well, and actually a 5th one here if you count the origin. So there's actually 5 corner points for this one. And so if you take each one of the corner points that you get and you plug them into the objective function, you should get a maximum profit of $2,265, and that occurs when x1 is 15 and x2 is 9. That was just a copy and paste. That just shouldn't be there. So the number of kilograms of solvent 1 is 15, the number of kilograms of solvent 2 is 9, and that's your solution. In the next section, we'll talk about how to solve linear programming problems using algebraic means.